Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from integrals, right? And here we are going to solve one important definite integral in which the greatest integer function is involved, right? So here we have to evaluate this integral in which we have to integrate this function, that is greatest integer of pi square plus greatest integer of 2 sine x from 0 to pi by 2, right? So here we are going to use the method of substitution, and let us start, and let us first take this integral as I, right? So here we are going to make use of the method of substitution, and let us take t is equal to 2 sine x, right? So here we are assuming t is equal to 2 sine x. Let us differentiate it. So we'll have dt over dx is equal to 2 cos x, right? And see, from here we have sine x is equal to t over 2, and from here we have 2 cos x, so we can write it as 2 times square root of 1 minus sine square x, right? Because we know the identity, that is sine square x plus cos square x is equal to 1, right? So now here we can substitute t over 2. So we have 2 times square root of 1 minus t square over 4, and if we simplify it, we'll get 2 times square root of 4 minus t square over 2, and 2 and 2 get cancelled, so we are left with square root of 4 minus t square, right? So dt over dx is now equal to 4 times square root of 4 times t square, right? So dx can now be written as dt over square root of 4 minus t square, right? So now we have this expression. So for dx we can write this expression, and now here in the original integral we see that x varies from 0 to pi by 2, right? So let us change the limits accordingly, because here we are assuming t is equal to 2 sine x. So when x is equal to 0, t is equal to 2 times sine of 0, and sine 0 is equal to 0, that is 0, right? Okay, when x is pi by 2, then t is equal to 2 sine pi by 2. So we have 2 times 1, because sine pi by 2 is 1, so this is 2 ones are 2, right? So when x varies from 0 to pi by 2, t varies from 0 to 2, right? So now this integral can be written as I is equal to 0 to 2, and here we have greatest integer of pi square plus here we have greatest integer of 2 sine x, and for 2 sine x we can write t. So we have greatest integer of t, and then we have dx, and for dx we can write dt over square root of 4 minus t square, right? So now we have to evaluate this integral, right? So here we see that we have the greatest integer of t, right? And the limits are from 0 to 2. So here we have 0 and here we have 2, right? And we know that whenever we come across with the greatest integer function, we search for integers, right? So between 0 and 2 we have the integer 1, right? So what we will do, we'll break this integral as a sum of two integrals. So the first integral goes from 0 to 1, and the second one goes from 1 to 2, right? So now we can write this integral as 0 to 1. Here we have greatest integer of pi square plus greatest integer of t, and we have dt over square root of 4 minus t square, right? And the second integral goes from 1 to 2, so we have 1 to 2 greatest integer of pi square plus greatest integer of t, and we have dt over square root of 4 minus t square, right? So now we have the sum of two integrals, right? Now what we will do, here we see that in the first integral the value of t lies between 0 and 1, right? Because t goes from 0 to 1, and in the second integral the value of t lies between 1 and 2, right? So if we take the first integral, then we see that the value of t lies between 0 and 1, so obviously the value of greatest integer of t when t lies between 0 and 1 is 0, right? So here we'll have greatest integer of t as 0, and in the second integral t lies between 1 and 2, so the value of greatest integer of t must be equal to 1, right? Because from the definition of greatest integer function, we can write greatest integer of t as 0 when t lies between 0 and 1, and greatest integer of t takes the value 1 when t lies between 1 and 2, right? So now these two integrals can be written as 0 to 1. We have pi square plus this value is 0, so we have pi square plus 0, that is pi square, and we have dt over square root of 4 minus t square, right? And in the second integral we have 1 to 2, and see here we have greatest integer of t as 1, so here we can write 1, so we have pi square plus 1, right? And we have dt over square root of 4 minus t square, right? So now we have these two integrals, right? And here we see that in the first integral we have greatest integer of pi square, right? So let us first assign value to this greatest integer of pi square, and we know that the value of pi is approximately equal to 3.14. so when we square pi, we get a value which is close to 9.85, right? So the value of greatest integer of pi square can be written as greatest integer of 9.85, and from the value of from the definition of greatest integer function, the value of greatest integer of 9.85 is equal to 9, right? So here we can write 9, right? And let us take the second integral. So here we have greatest integer of pi square plus 1, and see pi square is roughly equal to 9.85 plus 1 here we have, and if we add these two terms we get 10.85, right? And from the definition of greatest integer function, the value of greatest integer of 10.85 is equal to 10, right? So here we can write 10, and now these two integrals can be written as 0 to 1. Here we have for greatest integer of pi square we can have 9, so we have 9 dt over square root of 4 minus t square, and here we have 1 to 2, and for greatest integer of pi square plus 1 we can write 10, and we have dt over square root of 4 minus t square, right? So now let us find out the values of these two integrals, and see here we can write I is equal to, we can take 9 outside the integral, so we have 9 0 to 1 dt over square root of 2 square minus t square, right? Because this 4 can be written as 2 square minus 4 can be written as 2 square, and we have 2 square minus t square. Similarly here we have 10, we can take 10 outside the integral. Then we have 1 to 2, and we have dt over square root of 2 square minus t square, right? Okay, so now we have a simple formula, that is from integration. We know that integral of 1 over square root of a square minus x square is equal to sine inverse x over a, right? So we know this result from integration, and here we can apply this rule to evaluate this integral and this integral. See, here we have 2 square and here we have a square, right? And for t we have x. So now we can write it as 9 times. We have sine inverse of x over a, right? So here we have t and here we have 2, so we can write t over 2, and the limits are from 0 to 1, and here we have 10 times, and we can write sine inverse t over 2, and the limits are from 1 to 2, right? Okay, now we can substitute the limits. So we have here sine inverse of half minus sine inverse of 0 over 2, right? And in the second integral we have sine inverse of 2 over 2, that is 1, and minus sine inverse of half, right? Okay, so now we can write 9 times sine inverse of half, and we know that sine inverse of half is pi by 6. So here we can write pi by 6 minus sine inverse 0 is 0. Then we have 10 times sine inverse of 1 is pi over 2. So here we can write pi over 2, and for sine inverse half we can write pi by 6, right? So now we can simplify these two terms. So we have 9 pi by 6, then we have 10 pi by 2 minus 10 pi by 6, right? And 9 pi by 6 minus 10 pi by 6 is minus pi by 6 plus 10 pi by 2. So this is 2 5s are 10. So here we are left with 5 pi, right? And now if we simplify it, we'll get minus pi plus 30 pi over 6, and that is 29 pi over 6, right? So the value of this integral is 29 pi over 6. So viewers, this is how we can solve these type of integrals.